Welcome to solverfy.
Hi guys, my name is Julian, and I'll be helping you solve today's linear algebra problem. So we have these four polynomials. We want to show that these four polynomials are a basis for P3, the vector space of all polynomials up to degree 3. Our requirements for a basis are that a set of vectors spans their vector space and that they are linearly independent. So for them to span a vector space, that means that any vector in our vector space V, right? So any V in V can be represented as a linear combination of our basis vectors, or hypothetical basis vectors in this case, and that our hypothetical basis vectors are linearly independent, so they cannot be written as a linear combination of each other. So as long as we can check off both these boxes, that means that our set of vectors is indeed a basis. So let's try and check off the spanning requirement first. So first we grab an arbitrary polynomial from P3, right? And any polynomial in P3 will look just like this. And so now we want to set up an equation. So we want to set up a linear combination of these boys to equal our right-hand side here. So we'll just grab some arbitrary constants, and we'll call them bi, 1 b0, 1 plus x, plus b1, 1 minus x, plus b2, 1 minus x squared, plus b3, 1 minus x cubed. And we'll set that equal to p3 of x. And so let's expand this out and then collect our terms by degree. So we get b0 plus b0x plus b1 minus b1x plus b2 minus b2x squared plus b3 minus b3x cubed, and this should equal our arbitrarily selected P3. And mind you, these are arbitrary constants, so these AI could be anything. And that's precisely what makes it an arbitrary vector. And so let's collect our terms by degree now. So we only have one term of degree 3, and that's negative B3. And then we have one term of degree 2. And then we have two terms of degree 1. So we have b0 minus b1 times x. And then we have 4 terms of degree 0. We have b3, b2, b1, and b0. So plus b0 plus b1 plus b2 plus b3. And this has to equal a3 x cubed plus a2 x squared plus a1 x plus a0. And now we have a system of equations where we can equate coefficients. And this is a common strategy. I'll say equate coefficients like this whenever you're solving problems of this nature with polynomials. So we have negative b3 has to equal a3 because the degrees are the same. And then we have negative b2 has to equal a2, and so on. And then we have b0 minus b1 is equal to a1. And then we have that this sum equals a0. So b0 plus b1 plus b2 plus b3 is equal to a0. So what we can do is we can write this system as a matrix and then see if this system looks consistent or not. So to write this in matrix form, it would look like this. So, and let's do it from this way. So b0, b1, B2, B3 is equal to A0. Then we have B0, negative B1, 0, 0 is equal to A1. And then we have negative B2 is equal to A2. Let's just put some zeros here. And then we have that negative B3 is equal to A3. And so now we just want to see if this matrix is consistent, i.e. we perform Gauss elimination on it. And let me just make some space really quickly so that we can, there we go, have some space for our matrix up here. Alrighty. And as I said before, we're just going to do Gauss elimination on this matrix. But after just one operation, it should be clear this matrix is actually consistent. So we're just going to eliminate the pivot position right here. Or we're just going to eliminate that column for that one. So B0, B1, B2. I don't like the way I wrote those, sorry. So B0, B1, B2, B3.